Okay, so what I would like to start now is a new chapter here in the course where we are looking into recursive state estimation. So what we have done so far is basically we have a chunk of data which is assumed to be given, and then we use this data to perform state estimation. So for example, to estimate where the camera was when recording a scene, or where the camera was and where there were the location of distinct features or points in the environment. So we assumed always to have all the data given beforehand, and we want to do state estimation and estimate what the state of all elements at all points in time is. Often we're also interested in solving a slightly different problem where we say we have all the data up to a certain point in time t, and we want to estimate only the state of the system at time t. And as the time evolves, we want to update our state estimate from what the state of the system was at time t to what is the state of the system at time t plus 1. So we want to evolve our belief about the state of a dynamic system and update it according to the new measurements. Of course, we could take a naive approach and say we simply take all the measurements we have up to time t and do our standard estimation procedure. Perform state estimation, and then the next point in time is, okay, now we are only estimating the state of the system at time t plus 1, and we start completely from scratch using all the data up to time t plus 1. And at time step t plus 2, we do the same thing. We throw everything away what we have done. We say we take all the data up to time t plus 2 and compute the state of the system at time t plus 2. But this can be seen as very suboptimal because we're basically throwing away a couple of the computations we have already done. So what I want to look into here is a different approach, which is recursive state estimation, where we try to evolve the belief from time t to time t plus 1, only taking into account the new observations and the new information we get in. So we assume to have a belief, for example, at time t, having incorporated all the measurements from the first point in time to our time step t, and now we want to evolve this to time t plus 1. So I want to update my belief to go from xt to xt plus 1, taking only into account the new observations, for example, that I obtained, plus the belief I had before. But I don't want to touch, let's say, all the old observations again. So that I can very efficiently update my belief and estimate what the state of the system at the next point in time is. And this is kind of a recursive state estimation. So we take the result that we have so far at time t and want to evolve it to time t plus 1, only taking into account the new information we get in. And this is kind of one form of recursive state estimation. You want to do this based on a concept which is called the Bayes filter. So you may have seen instances of the Bayes filter already, for example, in form of the Kalman filter or the extended Kalman filter. This is one form of a Bayes filter. And we'll also see very soon why it is called the Bayes filter. And my goal is really to derive the Bayes filter from scratch and then show one very popular instance of the Bayes filter, or even two, which is the Kalman filter family, and I will introduce this topically differently compared to how Heiner Kuhlmann does it. So there are different ways to introduce this. I will start this category from Bayes statistics and see how we can end up at the result of the Kalman filter as a technique for doing recursive state estimation in the case where we have Gaussian distributions and linear models. It's a standard Kalman filter. But for today, I really want to focus on the general framework of the Bayes filter without going into kind of a specific implementation of the Bayes filter, and then also represent typical models that we will then use for the remaining part of the course on how to incorporate the sensor information in such a Bayes filter. Okay, so we start with the general problem of state estimation. So we're interested in estimating the probability distribution about the state x given observations and control information. So that means we are observing some information which tells us something about our state. This information is called that. And we can also change the world. And this happens via the control or via the action. So we have an influence on how we change the world. For example, if we have a camera, that would be the camera image that we obtain. And the action U would be how I move my camera. So if this is my camera, and from time step 1 to time step 2, I move it by, let's say, 1 meter forward, this approximately 1 meter forward movement would be that control. Of course, this can be noisy, but this is the control input. So I have a control input, so I can change the world, or someone changes the world, and I know how this world is at least intended to be changed. And I have the observations, and I want to learn something about the state of the system I'm interested in. So far, we did that by saying whatever the whole state of the system from time to 1, from 1 to t, taking all observations from time 1 to t, and all control commands from the beginning to the end into account. That's what we've done so far. And what we want to do today is to say we are only interested in estimating the state of the system at time t. So we are not interested in the state of the system in the past. We only want to have the current state of the system. And then come up with a formulation where we can formulate the state estimation problem as a recursive problem. And then we have our recursive term, so our previous state at the previous point in time, and then some updates of this state. This is kind of the goal we want to end up with. And we start with a very fundamental definition, so it's kind of the definition of the belief. There's nothing else. It's the state of the system at time t, given all the observations. So there's a sequence of observations from time 1 to time t, and the corresponding control commands. And this is what we want to add. We want to find a formula for this belief which has a recursive structure. So we, at some point in time, want to have something like belief of xt minus 1 and then some remaining part of that. And if we have that, we actually obtain our recursive formula. Okay, so what I can do right now, so you don't have to copy that down because you will find it on the slides, but I thought it may be worth deriving, very good, for deriving the equations for the Bayes filter really completely from scratch. So we start with p of xt given that 1 to t, u1 to t. So again, that are observations taken at time step t, and u are the control commands issued at time, at the corresponding time step. So actually how we reach, so ut tells us how we go from t minus 1 to t. Okay? Okay. So the first thing that we do here, we apply Bayes' rule, and this is also the reason why this thing is called the Bayes filter. And we use it to kind of swap xt and zt over here. So just use, I have a normalization constant from Bayes' rule, and then this is p of zt, so I move zt over here, given xt, so these are the two variables I'll swap. Then I have all my observation from time step 1 to t minus 1, because zt was moved over here, and the control commands which are not touched. Okay. Then I have a second term. What goes into the second term of Bayes' rule? Any idea what that was? How did Bayes' rule look like? So it's now state xt, and then we were sitting there in the background knowledge. Everything else except zt. So we have here that 1 to t minus 1 u1 to t. Okay? You can still see that over there? Everyone happy with this? Sorry? So there's a fraction, but this is just a normalization constant. So because it's not affected by the state. So this is just my normalization constant which encodes this. Okay? Okay, now just check. This is what we see here. Looks pretty similar, looks exactly the same. So everything which is red underlined here is kind of the part of the equation that has changed. So I turned this expression, via Bayes' rule, into this expression over here. Okay. So the next thing we look into is we look into this expression over here, or this one over here. We say, okay, we assume here the likelihood of the observation at time t, given we know the state xt, plus some information about the past. So what we typically do in this situation is we exploit the Markov assumption thing. Given we know the state of the system and then what we observed in that state, it's kind of independent of what was happened before. Okay. Given the knowledge of the state, so given xt, this part over here is actually independent from the observation. So again, if we know the state, we decouple the observations we get from this point in time on and from the past. Okay? Markov assumption, you should know, right? So okay, the assumption is if we know the state of a system at one point in time, we have the full knowledge about the state. Whatever we observe from this point in time on or anywhere in the future is independent from what we observed before. Because the knowledge about the state renders them independent of each other. So they are conditionally independent given the state. As a result of this observation at time t is independent from what I've seen before. But again, this only holds if I have full knowledge about the state. So we can simplify this expression to p of zt given xt, and the remaining part is actually independent. So it's independent. This is the same expression. Because given we know the state, those things which happened in the past are independent from the future, what happens from point in time t on. And the rest is just copied over. P of xt given z1 to t minus 1, u1 to t. Okay? And the thing which is called the Markov assumption that we have in here. Okay, now we said, okay, we kind of simplified this term substantially. Let's have a look how we can actually simplify this term over here. Is there a chance to kind of, not necessarily simplify this term, but kind of simplify these parts of the expression over here? So especially if I'm interested in doing this, have a recursive estimate, I need to have all the terms should resemble either something which happens at time t, or, which is this one over here, or something which tells me how I move from time t minus 1 towards t. Because this is kind of the update step to update my belief from t minus 1 to t, or from t to t plus 1. So I may want to couple entities which are just one time step off. So here I'm interested in estimating xt, but there's no xt minus 1 showing up here in the given part of this expression. Which would be nice, because if I would have an xt minus 1 in here, this is kind of just an update how to go from t minus 1 to t. So it's one of these small steps, kind of the increment over this recursive estimate that I try to develop. So how can I put an xt in here? Kind of want to change the expression, rewrite the expression, of course, without changing its value, but getting an xt in here. This is one of the standard rules of probability theory. So you have an expression, P of A, and you want to change this in some form that in here only P of A given B shows up, and not P of A alone anymore. How could you do that? So what I have to add to this expression well, there's something which is called the law of total probability. So that means, can we multiply this term by P of B? I need to integrate over B. Okay? And this is the same. Of course, this is basically the joint belief, and I integrate out the variable B. Okay, so we can now directly apply this expression over here to this expression down here, where A equals xt and B equals xt minus 1. If we do this, we have our normalization constant, our first part which does not change. Then we have the integral of p of xt given xt minus 1, the thing I added, plus all the background knowledge, that 1 to t minus 1, u1 to t, times this expression p of b, to the next line, p of xt minus 1, and the background knowledge stays the same, t minus 1, u1 to t, dxt minus 1. Okay? So it's just basically copy-paste what I've written there, except that I have additional background knowledge. So kind of given some background knowledge C, can add this to all the expressions. So this is the background knowledge, this is B, this is A. And then I end up with having this expression over here. So the key thing I gained here is that I have this expression over here that says, it tells me something how I evolve the state from xt minus 1 to xt. I want to make this transition from xt minus 1 to t, which is the thing I want to have for my the recursive update of my belief. See if x is the same here, apply the law of total probability, and we end up obtaining this expression over here. It's exactly the same what's written down here. Okay, now I may want to look into this term here again, this part over here. Or here, this expression down here. And I want to simplify it again. How can I simplify that? Applying a very similar trick that I have applied already beforehand. Yeah?
You know the state again, so yeah, you don't need the observations from before.
Exactly. So I know xt minus 1, I know the state at time t minus 1, so I can discard everything which happened at xt minus 1. The only thing I can't throw away is ut, because this is something which didn't happen in the past. So I can simplify this expression to normalization constant p of zt given xt, my integral. So I can throw away all this information except ut. So I have p of xt given xt minus 1 ut times this part down here. xt minus 1 given that 1 to t minus 1 u1 to t dx t minus 1. Okay? That's exactly what we've done here, Markov assumption. And now I say, okay, this expression is sufficiently simplified. This is just everything which happens at time t, which is fine. This is something which tells me how to go from t minus 1 to t. And I have this part over here. That this part over here looks similar to another expression you see on this slide. Not the same, but similar. Yeah?
Starting point?
Exactly. So this expression here looks very, very similar to the starting point. The only difference is this variable ut. This would be ut minus 1. It would be exactly the same, except that the whole index is shifted by 1. So what I now do is an independence assumption. So I'll make an assumption which is not correct, not fully correct. We can discuss if this is a good or a bad decision. But simply saying, I simplify this term, saying this is approximately the same than replacing this t by t minus 1. So I'm applying an independence assumption. Say, okay, I just replace this guy here by u1 to t minus 1. So I make an independence assumption. So I'm replacing this guy over here. So why can I argue that this may make sense? What I'm doing here, I'm interested in estimating the state of the system at time t minus 1, given all the observations up to t minus 1, given all the controls up to t minus 1, so everything which happens, plus a future control. You can say, for estimating what the state of the system is at time t minus 1, what I execute in the future, the commands, how I move my camera in the future, doesn't really help me to estimate the state of my system at time t-1. And can you argue that this is a reasonable assumption? In most of the situations, this UT will not help me to gain some extra knowledge about where the system was at time t-1. Most of the time. If you have an example that, let's say, at least some intelligent person is moving the sensor, if you estimate that your system is, for example, it's either here, or let's say, it's either here or here. These are the two beliefs that you have about your camera, or the person holding a camera. So you don't know, am I here or am I here? The two beliefs that you may have. Now, if the next command is move 1 meter forward, 1 meter forward, possibility number 1, or here, possibility number 2, move a meter forward, I would bump into the table. Assuming that a reasonable person holds a camera which cannot walk through tables, this state is very unlikely and this state is much more likely. So these are kind of situations where executing the motion command T would lead to an invalid state. Then UT can tell me something about the state at xt-1. But these are very, very few situations where this is typically the case. Therefore, in most of the cases, it is a reasonable assumption. But again, we need to make sure this is an assumption that we are doing here. It's an independence assumption. We are assuming independence. It's not necessarily correct, but it simplifies our life. And we can argue that the approximation error is likely to be small. If we do this, now, this expression is exactly the same as this expression over here, except that the index t is replaced by the index t-1. So that means this can be rewritten as simply the belief at time t-1. So I can simply rewrite this as the belief at t-1. And now I have exactly this recursive expression that I was looking for. What this expression tells me is, if I know the belief at time t-1, and I know the current command which has been executed, and I know the current observation that I get, this expression evolved the belief from time t-1 to time t. And this is great. So assuming that how the state evolves from t-1 to t is something which is independent from what happened before, how I evaluate the current observation given the current state doesn't depend on the past. So these are typically two things which can quite efficiently be computed because they don't depend on everything I did so far. And of course I have my recursive belief. But what I can do with this expression, I can continuously estimate the state of the system without, for every update, considering everything which has happened in the past. So at every point in time, I only have to do these computations over here. And this is kind of the stuff I've done before, I've done already. So I can exploit my previously done computations in a very efficient way to evolve the state from time t-1 to t and have this recursive state estimation. So what you've seen here is really the full derivation of the Bayes filter, starting from what I want to do some assumptions or some modifications of the equations. I do an independence assumption, and I end up at this expression down here. Okay? And this is the basis for a lot of different implementations, filtering approaches, that are based on this so-called Bayes filter. For example, the Kalman filter is one of those examples, which is a very prominent example. We have things like discrete filters, where we use histograms to estimate quantities. We can use particle filters, which you haven't seen, but may have heard of or seen in one of the talks that I gave here about a different form of state estimation, where you can deal with non-Gaussian beliefs in a very efficient way. These are all implementations of this basic concept of this Bayes filter. What we can do is, or what is often done, is to kind of break up this expression into two parts. And most of the time it's actually broken up here. By saying this step over here is a step which only takes into account observations, and this is the part which only takes into account the recursive part and the command that I used. So this is an a prediction step where I use a control that I send to predict where the system is likely to be. And this is an update step where I take into account the observation to update my prediction. Therefore, if you look at the literature of a Bayes filter, you often find this prediction step and you find this correction step. And this, you see it's just broken up the equation in two parts. The one starting from the integral, this is the prediction step, often written as belief bar. So this is a predicted belief about the system at xt minus 1. This is the part which only takes into account the control. And then we have a correction step where we use this predicted belief and incorporate the observation to obtain our real belief at time t minus 1. And again, this is our recursive part. This is something which tells me how the control is used to update the belief, the prediction step. And this is the correction step, how the observations are used to correct the belief that I have. And therefore, this part is often called something like motion model, because it tells us how the belief or how the control updates our state, which is often a motion, doesn't necessarily has to be a motion, but this is where the name comes from, how the motion updates the state of the system from time t minus 1 to t. So if I have my camera and I say, okay, I take my camera and I move it approximately a meter forward. This is actually this motion command. This is my prediction where the camera is without taking the observation that the camera makes into account. And then the correction step assumes the belief that the camera is here and then updates this prediction based on the images that we get and updates the position. This is something which is called often observation model or sometimes sensor model or measurement model, which says what's the likelihood of the observation given the state. And so the different implementations of the Bayes filter that exist implement those different aspects differently. So some make some assumptions about these probability distributions. Some say they all must be Gaussian distributions. Something the Kalman filter or the whole family of Kalman filter approaches do. There's one assumption that we can do. Other approaches say, okay, these models here must be actually linear models. Again, an assumption that the Kalman filter does. Or we use linearized versions of this model. Or we say we allow for nonlinear functions over here. Or we don't restrict ourselves to Gaussian distributions and want to take into account arbitrary forms of distributions. And this will lead to completely different implementations of this Bayes filter, which follow the same ideas, but can, from the implementation point of view, be completely different. Because say, if these are all Gaussian distributions, we only need to estimate a mean vector and a covariance matrix, which can typically be updated quite efficiently. If you use different forms to represent distributions, this may turn into a very complex and completely different algorithm. So the key thing is there, the Bayes filter is just a framework on how to do recursive state estimation, and the individual implementations or realizations can differ substantially, and as in Gaussian distribution, linear or nonlinear models. In this course here, we'll look into one special implementation, which is a Kalman filter or extended Kalman filter. In the remote sensing course, in the master program, we look into different approaches for non-parametric estimation, state estimation, where we don't want to restrict ourselves to Gaussian distributions and where we don't restrict ourselves to linear models or models we can linearize very well. So a more general form of state estimation, which has a lot of advantages, but of course also some disadvantages. Here, we are looking into Gaussian distributions. So all these guys over here, this expression, everything is Gaussian. That's what we assume. And we assume linear models, so a linear motion update, for example. And this then will lead us next week to the Kalman filter, where we'll derive the Kalman filter and see how we end up in one form where we can do recursive state estimation. What I now want to do is I want to look into two specific, or a few typical implementations of how a motion model could look like and how such an observation model can look like. So the motion model again was this expression over here. So how I turn my belief from time t minus 1 into the predicted belief. So how do I model, what's the probability distribution that the state of the system is xt, given I know it was before at xt minus 1 and I know which command has been executed. So it's, for example, like I'm a car, relating to the talk Ingmar will be giving on Thursday. I'm a car, I'm at a certain position at time t minus 1. The person is pressing the gas pedal at a certain level for 1 second. Where am I after that second? So I can estimate, okay, what's the current speed of the car, how long had the gas pedal been pressed, how strong has it been pressed. So it will lead me to some believe that I'm probably here, but maybe a little bit further or a little bit back, depending on the angle of the steering wheel. I may have turned a little bit to the right or a little bit to the left-hand side. And this is exactly what this probability distribution is describing. Given I know where I was at time t-1, given the steering angle and how the gas pedal was pressed, where I'm going to end up with. And this is a probability distribution. So by executing this motion, I typically increase the uncertainty about where the system is. When we think about a Gaussian distribution, if I'm here at xt-1 at a very focused or centered Gaussian distribution with a small covariance, or small variance, let's say I'm just in 1D with a small variance, and I move forward, I typically increase my uncertainty V, because I add noise to the system. The motion execution is not perfect. If motion execution would be perfectly noise-free, absolutely perfect, the variance should actually stay the same. But as this is typically not the case, I increase my variance in most of the setups that I have. Okay. So we need those motion models in this probabilistic estimation because motion is inherently uncertain, and the question is how can we represent this uncertainty? So what you see here is an example of a trajectory starting over here. In this case of a mobile robot, this was one of the early competitions. A robot going through a maze, exploring a maze. And this is a trajectory that the robot was taking, kind of the true trajectory. If we just take into account the commands that we have sent to the platform, or even if we take the wheel encoders at the wheels, which simply measure the revolution of the wheels and say we take what those wheel encoders tell us at the motion commands that we send. This motion is uncertain. And this ends up in a trajectory estimate which looks like this. So the platform started over here, moving around. And you can see there's a drift in here. The platform is drifting to the right-hand side. Or at least the estimate of where the platform goes. So we need to compensate for that. So we have to model the motion as a probability distribution. And this probability distribution is exactly this motion model. So how do we describe the uncertainty, how to evolve the state from xt-1 to t given only the motion command? Okay? So we start with a simplified form of motion on a plane. So I don't want to go into 3D. It's fine if you can draw the stuff in 2D. And consider we have a vehicle which can drive forward, backward, and it can rotate. So for example, we can see there's a platform with two wheels, one on the right, one on the left-hand side. If we turn both wheels in the same direction, we're going forward. If we turn both wheels in the reverse direction, we go backward. If we turn one wheel in the backward direction, this in the forward direction, we're actually turning. And if we turn one wheel slower, this one faster, this one slower, we will drive on a curve. So the system has a state in terms of an x and y location on the plane and its current orientation where it's heading to. So we can describe this as a system like this, or describe like this. So this is the x and y location of that system, and it has some orientation theta. So three-dimensional state vector, x and y location, and one orientation. And we may want to model the movement from time t equals 1 to t equals 2, how the platform can go up over, can move over there. So again, this is in second x prime, y prime, theta prime. I want to describe this motion, I want to describe this in a probabilistic way. So we take into account the uncertainty how to move from A to B. And in order to describe this motion, I have to have some control. This u, for example, we call it here, which describes me how I move from here to here. And there are different ways for describing the motion of such a platform. We can say it's a translation in x, it's a translation in y, and it's a rotation. It's one way for describing that. But there are other ways. One way is, for example, describing this first by a rotation, then by a translation, and then by a second rotation. Something called the rotation, translation, rotation model. So I have this in case as a rotation 1, a translation, and a rotation 2. This would be the first step Let me draw this straight line over here. This would be the rotation 1. This motion would be the translation. And then the system ends up staying here. And this is the second rotation. So, and by using these 3 parameters over here, I can describe how the system from any initial state turns into a second state. This is something which is often called the odometry model for the rotation, translation, rotation movement. Here again, this is how we start. So we have a rotation to the straight line distance connecting the first and the last position. Then we move on a straight line, then we rotate. Of course, in reality, this motion is typically different. So in reality, the motion is probably something, an arc like this, but it's more complex to describe. And we would need more parameters, not the minimal number of parameters to describe the translation from this state to this state over here. So we make the simplifying assumption. We have a rotation, translation, and rotation model. And this is the equations, how we actually compute that. So the translation, the distance we need to translate is just the Euclidean distance between the 2 centers, should be pretty clear. And then the first rotation is basically given by 2 things. So this etan2 function tells me the angle of this line over here with respect to the x-axis. That's the x-axis going over here. So this would be this angle, the etan2 expression, and then the difference, the orientation of the platform before. So this would be a negative angle in this situation. I'm subtracting it so it gets added up. So this is my first rotation. And then the second rotation is just where I ended up with as my rotation 1 and how much I need to rotate to enter the final rotational state that I want to be in. So it's really first rotation, translation, and second rotation. Okay, so I said this is kind of my model, how I evolve from my current state to the next state. How can I express the an uncertainty in this movement? Because I want to end up with a probability distribution. And one model to do this is say, okay, I see this as a rotation, as a translation, and a rotation, and I have noise in this translation and in this rotational steps. And I can assume, let's say, a Gaussian distribution in the noise. So I have a Gaussian noise in my rotation here, I have a Gaussian noise in my translation over here, and I have a Gaussian noise in my second rotation over here. So we can say again, this is a probability distribution where I have an uncertainty over here, an uncertainty over here, and an uncertainty over here. Okay? If I do this, do I end up having a Gaussian distribution in terms of my probability distribution? So that I have individual movements here, they are all assuming to be Gaussian noise. Will this lead to a Gaussian distribution about this state given I know this state over here? Yes or no?
I think I forgot my question.
Okay. Okay. So we are here in that state. We assume to have some Gaussian noise over here, some noise along this direction, and some noise over here in this rotation. Will the distribution about this state be a Gaussian, yes or no? No, it will not. For what reason will it not be a Gaussian distribution? So these functions involved in here are nonlinear functions. And if I take a Gaussian distribution, kind of squeeze it through a nonlinear function, the result is not a Gaussian distribution anymore. And if we take this form parameterization, we get distributions which look like this. So dark values means high probability, bright values mean low probability. So to move from here to here, we get kind of these kind of distributions. And it's something which is often called a banana-shaped distribution, because it really kind of has a banana shape. So what you can see in here, in this kind of distribution, we have noise in the translation and noise in the rotation. So you can see kind of moderate banana shape over here. In this example over here, we have a stronger noise in my translation, a smaller noise in the rotation. And kind of gets more into a Gaussian shape, although it's not perfectly Gaussian. And here we can very precisely execute our translational movement, but a very noisy in our rotations. So we have a very kind of strong banana shape, or circular arc shape over here, which kind of moves away from the Gaussian distribution. And this is kind of, if I would conduct, whatever, 300 experiments, would start with the platform over here, execute the motion. These are the dots where the system, where the final state will be. This is what actually this probability distribution generates. So these are kind of hypotheses. If I'm here in this state and execute this experiment, give the same motion command, whatever, 300 times, these are the locations where the system is going to end up with. But what I have, if I use this form of describing my uncertainty between the two states of a system with this form of transformation, rotate, translate, rotate, with Gaussian noise, I actually end up having these types of distributions. And this is one of the standard distributions which are often used for simple movements on a 2D plane. So this model may change to some degree, for example, if you use a car, you want to model a car. The problem with a car is that a car, at least most implementations of a car, cannot turn on the spot. So what you have a steering angle, and then you have to give a motion command, and then you drive on an arc, and the steering angle is limited. To take that into account, this model of how to move from here to here gets more complicated, because a car cannot rotate on the spot, drive forward, and then rotate on the spot. So you have constraints in your motion, and then you need more complex ways for describing this transformation. But this is one of the most simple forms of so-called odometry-based motion model. Well, this was also called a differential drive platform. So you assume to have only two wheels, maybe some stabilizing wheels, and you can move them freely. So again, one wheel rotates in this direction, the other one, the reverse direction, you actually can turn on the spot. So kind of one of the very, very simple forms of describing motion on a plane. And this probability distribution, this distribution over here, is one way to describe this motion model. So P of xt given xt minus 1 and ut. And then this is xt minus 1, ut is not shown here, it's the command that I execute, and then this is the resulting probability distribution. Okay? Okay, and now we did the very simple motion model. Next thing is, let's look into the very simple observation model. So this is this part of the expression, P of zt given xt. So given I know the state, what's the likelihood of obtaining a certain observation? So I don't want to start with camera right now. I want to take a more simpler sensor for building up those models. Let's start with the laser scanner. Just see the device which can measure an orientation and the distance to the object at the same point in time. Like the camera that we have, but the camera only, we have a distinct point, only gives us a direction to that point, but we now also want to get the distance. With one single measurement, not triangulating with from two different views. So we have a simplified model. And what we have typically, we have a number of laser measurements. For a certain number of directions, we get a proximity measurement. How far is the current obstacle away? So one scan, ZT, consists of k individual beam measurements. So if we have a 2D laser scanner, for example, in the simplest form, it's basically a mirror that is rotating. So let's say a 45-degree slanted mirror with the laser diode over here. The beam is reflected, and through the rotation of the mirror, I actually measure the time it takes for the light to be reflected by the object. I measure the signal again, and the time difference tells me how far the object is away. Simply have a rotating mirror, which gives me a 2D measurement in the plane. Depending on how often I pulse this laser, I get a different number of those beams. And so I get k proximity measurements in one single scan. The first key assumption is done for most of those scanners is that these individual measurements taken at different directions are independent of each other. So if they're independent of each other, so P of zt given xt, so M is kind of the map of the environment. So I assume I know how the environment looks like. Sometimes this was included in xt. Maybe it was suboptimal. Maybe I should take the M away to avoid any confusion over here. So it basically means we have full knowledge about the world. We know what the environment looks like. Then we say all these k measurements are independent of each other. So I can express this as a product of the individual probability distribution of the beams. So every beam can be treated independently from the full scan. So for the remaining thing, we only look into those individual beam models. So one measurement in one direction and the proximity measurement. So if I have this angle over here, what's the distance to this green spot there on the wall? And I get that measurement, and the question is, how do I model this proximity measurement? How do I model the noise involved in that? So the standard approach is something which is called a simple raycast model. We just say, okay, I know where that wall is in the environment. I'm standing here, so let's say this wall is in reality 5 meters away. So I assume to measure something like 5 meters with some variance involved in that. Let's say I have a Gaussian noise model. So then I say, okay, this is where I know the wall is. So if I measure that wall, I expect to have a distribution which looks like this. So just hand-drawn Gaussian, not the perfect Gaussian, just hand-drawn over here. So I said, I have some measurement noise in what I'm going to measure. And depending on the quality of my laser scanner, the variance may be smaller or maybe larger. But I have a Gaussian measurement noise in there. And this is the most simplest form of these types of measurements. So if I want to say, what is the probability of obtaining a measurement given I know the state of the world, which means given I know where the sensor is, given I know what the environment looks like, I can actually compute this probability distribution by saying, how far is the object away from the sensor location? And then, this gives me this point over here. And then I have a Gaussian noise of my sensor, and this is a property of the sensor. Basically, what the variance of this distribution. And then I have a probability distribution to describe the likelihood of an observation that I obtain in that situation. So this is kind of the expected observation, the expected measurement. So this is my probability distribution, which I use to evaluate a measurement that I obtain. If I obtain a real measurement, I can evaluate it under this Gaussian distribution. So it's kind of this idea clear which sits behind that. So what I have world knowledge. So I know where the sensor is supposed to be. I know what the environment looks like. What I can do is I can compute a predicted observation or an expected observation. What should I measure in this situation? I can simply compute this from the model. I know where I am. I know where the obstacle is. I simply can compute the Euclidean distance between those 2 points. And then I have a property which says I know something about my sensor. I know my sensor has a certain variance in its proximity measurements. So I generate a Gaussian distribution at the expected observation or predicted observation with the corresponding variance. And this is then my probability distribution about what I'm supposed to measure, given I'm in that state and what the world looks like. Okay? It's kind of the idea clear behind that. Okay, good. This again is a very simplistic model. What is not modeled in this simple, so it's called simple or simplest raycast model? Which effects are not modeled in such a situation? Yep. Systematic errors are definitely not modeled in here. What else is not modeled? Think about a realistic setup. So we go out there, build up our laser scanner, and take a couple of laser scans out there. Why will the distribution that we get probably not follow this form? If you look out there, let's say you put our scanner exactly now out there and take a scan. What will happen? This person will walk through our laser scan. So there will be unexpected obstacles, which simply show up in realistic scenes. If I don't build up a perfect, idle, empty scene before, we will have to account for unforeseen obstacles in the environment. Also things which may not be perfectly modeled. Let's say I know the perfect model of the world, but these two guys park their bikes out there. If I take a laser scan, some of the beams will hit the bikes, reflect the bikes, and this is something which is not in my model. So my model is likely to be not perfect. There may be additional obstacles which would be placed in there. Other things which can happen is that, for example, some of the beams actually miss an obstacle and go all down Musali. So actually the scanner will not receive any signal back. It will give an error reading or max reading, so no obstacle found in the maximum range of the scanner, or one of the effects I could have. Another thing I could have is that I just have a random measurement, something I haven't modeled well. So all kind of effects which can influence the distribution that I actually get. Therefore, people started building up more advanced those raycast models. So raycast means basically I'm following the ray and see where it could be reflected and build up a probability distribution out of that. What you see here is one of the forms. The distribution looks a little bit weird, but you can express it and actually reflects reality very well. So what you see here, this is kind of the predicted observation. So where you know there's an obstacle in the environment. So measuring anything behind that is actually very small, except this kind of peak here in the back, which is kind of the maximum range of the scanner, which basically means the object wasn't hit or the beam was completely reflected into a different direction. I simply get no signal back from the laser. There's simply something which happens, which is this peak over here. And then we have something Gaussian-like over here, which reflects my measurement noise, but I have increased probability of a reflectance over here. And this is something which comes from the dynamic obstacles. The weird thing is we kind of have this weird nozzle over here, which is not an artifact by drawing. It's actually something which you see in this distribution. We'll see actually in a second where it comes from. Okay, let's look into kind of, this is done by a mixture of different distributions, and we just would go through those distributions and discuss them so that you understand why we can end up with such a model. And this is a model which is frequently used, and it actually matches what you see in reality actually quite well. So the first thing is, the first component is our measurement noise. This is what we discussed basically. So with a Gaussian distribution centered around the expected observation. So it looks like this, Gaussian distribution, expected observation, and expected observation of the distance, known distance to the wall. So and then the probability for obtaining this observation given the pose that I know and given the world is simply a 1D Gaussian distribution, and simply what do I measure in reality, how much does this distance differ from my expected observation. And then it's a standard Gaussian distribution. So that's what I have in here. Should be clear, I guess, or if there are any questions, let me know, but I think that's a pretty clear case over here. The next things we may want to look into account is, oops, what happened here? The unexpected obstacles. So like the people walking around here in the scene, things which are unexpected in the environment. And I argue that this is an exponential function with an exponential decay looking like this, dropping at 0 at the expected measurement. So the thing is first, why it is 0 over here? Because I know, according to the knowledge of the world, that at that point in time there's anyway an obstacle. And so what this model says is actually the obstacles, the unexpected obstacles that are between the sensor and, let's say, the wall over there. So if I measure here in this direction, this wall, I don't care if people are walking behind the wall. I simply can't see them. So I'm only interested in the people walking in front of that wall. So the probability of seeing any person walking around behind the expected obstacle can be assumed to be 0, and I only have the probability of seeing people up here. So the question is, why is this an exponential function, exponential decay over here? There's something which is quite likely to be not clear. So why is this an exponential function? We assume we have a couple of persons in the environment, let's say up to n persons, and we assume they are randomly distributed, or objects, so people walking around, or objects which are placed. So we don't want to make any assumptions. We say they're randomly distributed over the space. And I still get this type of functions. Any idea why it has this kind of form? And it's not, let's say, a uniform distribution over the space. Huh?
Because it's a radius, and so the probability if a person is standing right in front of you.
Okay, this is a good idea, but it's actually not the case. Or at least it's something which is not explicitly modeling here. We can even, let's reduce it to 1D world. So we simplify our life, and we say we do the same thing along a beam in a 1D world. So we have our scanner over here scanning in this direction. And we have a uniform distribution of random objects and random objects here over the environment. Why is this function looking like an exponential function? Okay, so, I mean, it's not super obvious. I'm not expecting you to come up with the right solution, but it's kind of a very nice and intuitive description that we can find here. So let's, for simplicity reasons, just discretize the space. Like this. And let's simply say we have our objects which are placed at random locations. Here, or here, or here, or here, or here, or here. And what we're actually interested in is only the first obstacle. So if here is a person and here is a person sitting, I don't care about this person because this person will already reflect the beam. So what I'm basically interested in is the first person or first object seen from the scanner. This is a key thing I'm interested in. Not anywhere, just the first one. Okay, and now I can do this. We can make an analogy to bit strings. So you have bit strings. If you represent how you represent a number in your computer, an integer number, are basically bits of zeros and ones. And let's now treat this as a bit string. And kind of, if I flip, then they're all zeros, and I flip this to 1. If I flip this to 1, if this is 1, that means there's a person or an object. Then I don't care about anything which happens back here, right? Then I will get a very short measurement. What's the probability that this is happening? If these are kind of n-bit strings and I have up to n objects or persons that I can have in my space. If you treat the analogy to bit strings, you flip the highest value bit, so it's every number up to 50, the 50% of the numbers that you can represent with the string. So it affects 50% of the bit string that you could handle in here. So if of all possible combinations of objects being there or not being there, in 50% of the cases, this guy is 1. So for the first situation, so first bit, we have a 50% chance that there's a 1 or that there's a 0. It's the same, it's a symmetric. Okay? Now, let's assume I take the different case where the first bit is not set, it's a 0, and looking to the second bit, there's a next option which can happen. So it means here's no person, then there's a person, again I don't care about the rest. How many bit strings have this pattern? 0, 1, and I don't care about the rest. Huh? 25%. 50% times 50%. So second bit is, or a quarter. Half. Third, 0, 0, 1. Half times a half times a half. So it's 1 divided by 8. And so on and so forth. And you can actually see that you get this exponential decay. It can be represented by an exponential function. The reason for that is because only the first obstacle along the path matters. And if assuming a random distribution of objects over the environment, then I exactly get a function with an exponential decay. And as I'm not interested what happens behind the obstacle that I anyway know that is there, this is exactly the function that this is following. Of course, I need to determine the parameters, which depends on the space, on the size of the persons around and these things, but it should follow this type of function, but I still need to fit those parameters. Next thing, which can happen is actually a random measurement, something I haven't modeled, some random effect that I don't know. Assume simply a constant function all over all possible measurements, just for modeling all the effects that I don't exactly know. This value will be pretty small, this probability, or should be small in the weighted sum of those different components, but there's one way for modeling that. And then the last one is simply the max range or no return measurement. This is simply if I'm in a situation that an obstacle is too far away or that it's, for example, is completely reflecting the beam, what simply happens is the sensor reports either maximum range or an error code, which is typically mapped to maximum range. And then you simply have, basically means you have no reflection, so no light is going to be reflected back to the sensor. And if this happens, you don't measure anything, and you have kind of the highest probability of in this last bin over here. What you now can do is you take those functions and mix them together as a weighted sum. And then you get exactly this type of distribution. This was the exponential decay. We have our Gaussian. This kind of model over here is a weighted sum of the exponential decay function and the Gaussian distribution. The exponential decay function was going to 0 at the expected observation. It's exactly kind of this weird shape that you actually get. And the funny thing is, you can actually see this form if you look to real-world data. You can actually see this small nozzle over here. So the question is, this is a weighted sum of those 4 parameters. How do we actually determine the parameters of our model? So the weighted sum, and of course also the individual values like the variance of this distribution. What could we do to actually get those values? Any ideas? Simply record data and try to fit this function to the data that I get. So put a sensor in an environment, records hundreds or thousands of laser scans with people walking around, and then simply I will get different return measurements, and the question is, I need to simply adjust my parameters with some parameter or error minimization optimization scheme so that I end up fitting the data. And this is an example of measuring a proximity in one single direction. The expected measurement was here at 3 meters, taking 10,000 scans, and this is actually the distribution that we get. There were dynamic obstacles walking around, there were some reflections, and this is the result that we get. And what we now do is we simply take the parameters of this function and fit it to these types of data. And if you do this, we actually obtain those functions over here. And we see that they are different sums for different proximity measurements. So if the expected measurement is very small, that means the expected obstacle is very close to the scanner, a lot of the probability mass will be concentrated in this Gaussian distribution, because less probability is kind of taken away from the exponential decay function, which is different if the obstacle is further away. So the known obstacle is further away because there's a higher likelihood that people will actually distribute and populate the space. They can actually learn those parameters and in this way fit this type of functional parameters for this type of model. Again, this differs for different expected distances. You can express this in a functional way actually, and then you obtain this type of model which works very well in practice and actually reflects what you typically observe if you drive with a platform through a populated space. Fits actually very well to the observation that you get in reality. Of course, if you have a perfectly isolated scene taken under perfect conditions without any dynamic obstacles around, you may change those distributions, but that's something that you typically obtain in realistic or in populated spaces. So this was one of the most advanced models that you can use for, not the most advanced that you can find, but one of the more advanced models that you typically find. But people often have the tendency, in order to make things fast, to even look to more simpler things. And one of the things is even completely to avoid raycasting. So raycasting was the operation to actually check through my map if there's an obstacle along that ray. So I'm basically following that ray and looking for obstacles over there. And this is computationally a not that cheap operation. It can be done fast on graphic cards, for example, but it's not the cheapest operation you can do. So what you can do in order to further simplify that is use something which is often called the beam endpoint model. What the beam endpoint model does, it simply says, I don't trace this ray, so I'm not following again through the map through my measurement direction. I just say, I know what I measured. Let's say this was a measurement of, let's say, whatever, 5 meters. I simply say, I check in my map 5 meters from my location in this direction if there's an obstacle, yes or no, and just use this as an information if this beam is likely to be reflected by an obstacle or not. So I'm completely ignoring if there are obstacles along the path. So I'm not tracing the beam. So what you see here, this is the environment. You have whatever 2 pillars over here and a box with an obstacle over here. What you can do is you say, okay, I assume some noise in here, so you basically compute a smoothed version of this image, which you can see over here. So the white cells are basically a smoothed, for example, with the Gaussian kernel, smoothed variant of the original image. And then you simply take your beam, you look to the final location over here, and you take this smoothed value over here. If this has a large value, it means this beam ends up in an obstacle. So if here would have been an obstacle, this would be a white spot over here, or would be a white area over here. So it would be a high likelihood that it's a good score, because in the measured distance from the scanner, there is actually an obstacle. So that's good. Or if this is not the case, and it is shown here, that's bad, and this will give a low score over here. This model completely ignores that there may be obstacles along that path. So it's not a physically motivated model, because you're ignoring the fact that your beam doesn't pass through obstacles. The main advantage of this model is just that it's extremely fast to compute, because you just need to compute the endpoint and do one lookup in a map. So it's orders of magnitudes faster than the other models. And that's the reason why it became so popular. It also works surprisingly good, let's say it that way, although it's physically not well motivated. But it's just a very, very common model to use because it's so fast to compute. So as an example how this looks in reality, so if this is a map of the environment where every white cell represents free space and every black cell represents occupied space, is actually the map of a museum. And you kind of see different objects or booths standing over here. And then if you would turn that into this so-called likelihood field, so kind of in this type of representation, you would get a map like this. And you just need to take your measurement and simply check the endpoint. If it is in a bright cell, get a high score. If it is in a low cell, you get a low score. You just need to have one lookup in an image. You just basically need to query one single pixel, which is extremely fast to do. That's one of the reasons why those models are so popular. This can be pre-computed, this kind of likelihood field over here, very simply just by basically smoothing your image, and then just you need to look up one pixel, and that's it for your model, for your observation model. So it's extremely efficient. The other thing is if you want to look into landmarks, so if you're interested in, so you have a certain distinct number of landmarks in the environment, and you want to obtain your whatever range, you have any range bearing sensor, could also be, let's say, a stereo camera, and you want to estimate what is the probability distribution that you see this distinct point and how far it is away. You typically express this in a range and a bearing angle, so range and bearing. So you have a bearing or an orientation and a range. And then what's typically done, you have a Gaussian noise over this range bearing. And depending on your sensor, the range bearing is more noisy than the range. So the range component is more noisy than the bearing component. For example, for a stereo camera, you can actually localize the orientation of a pixel actually very well, but depending on the baseline that you have, you may not fix the distance to the object that accurately through the triangulation. And so the standard model again for the range. So if you know what this expresses is your expected observation, so the x and y and theta location is the location of your sensor. And then you have the map information about the J's feature, its x location, the J's feature, its y location. This is the Euclidean distance between the sensor location and the feature or the interest point that you're looking into. This is the expected angle that you're observing, and you simply add a Gaussian noise component to that. So this is kind of one of the standard model that you're using. If you want to use this and just want to use one single monocular camera, what would you do for that? So if you just use a monocular camera, not a stereo setup, just want to use a single image. How would this model change if you need to adapt this model? If you have a single image from a monocular camera, you don't know anything about the distance to that object. So basically, this information here becomes completely irrelevant. It basically means you put the variance of this component to infinity. And then you will only get some information. So basically this component doesn't matter, and the only component which matters is actually the orientation. So you would get only kind of 1 degree, so when we're living in 2D plane, 1 degree of freedom observation, so just one bearing, one angle, and no information about the distance. But you can still express this as a model. Which brings me to the end of the course today. So what we discussed today is basically what is a Bayes filter, so the basic elements of Bayes filter, which was a tool for recursive state estimation. So the goal was we want to update a belief about the state of a system, let's say at time t minus 1, to time t, only using the current observation and the most recently executed control command to update our belief. And the Bayes filter is one framework which tells us how to do that in a theoretical way. And what we'll look into next week is one specific implementation of a Bayes filter, and it's one which assumes Gaussian distributions and linear models in order to update this belief in an efficient manner. Every implementation of the Bayes filter depends on two quantities. One is the observation model and the other one is the motion model. What I tried here to do today is introduce at least some of the basic models that you can use if you have, for example, a platform moving through the environment. That's one of the simple steering models. With 2 wheels you can actuate, and you can basically rotate and drive forward, or do that even jointly. How does such a motion model look like? How do probability distributions look like if we have noise in those commands? Something you've seen. And how do models look like for some simple sensor modalities, which are very easy to formulate. It's like with a laser scanner. You can even take a depth image from a Kinect camera, so something which gives you orientation and depth information, or in theory even a stereo camera where you take 2 images, find your distinct points, triangulate them, and of course you have a higher uncertainty than in the depth information than with a laser scanner, for example. But you can fix the orientation quite well. And so these kind of different observation models, one instance of an odometry model, and the general framework of the Bayes filter, which I tried to explain you here. And especially the Bayes filter, the general concept of the Bayes filter is something which is very, very essential and something which pops up very often whenever you want to do recursive state estimation. So it's something that I value as really relevant for that course. So be aware that you know what the Bayes filter does and what steps are needed in order to derive the Bayes filter or to come up from the very basic definition of the belief towards the Bayes filter. If you want to read more about the Bayes filter, I can actually recommend the Probabilistic Robotics book, which has an excellent, from my point of view, excellent description of the Bayes filter. So there's one about the Bayes filter in general, and then also about some motion and observation models in those 2 chapters over here. So you find the book in our library upstairs, a couple of copies. And so it's, from my point of view, the best description of this recursive state estimation, or very easy to understand formulation of this recursive state estimation techniques. So that's it from my side. Are there any questions from your side which you haven't asked during the course? Did the question pop up again? Did your question pop up again? Okay. Anything? Yes, please.
So the likelihood here.
Yes.
Why was the whole obstacle white? Wouldn't it only be the border that should be white?
So it depends if you assume that your obstacles are solid or not solid. So the thing is, what the beam endpoint model says, I completely ignore what happens along the ray. It says I'm only checking at the endpoint. So if you're inside a wall, it's basically your assumption, is the wall supposed to be solid or not solid? And the assumption here was the obstacles are solid. But if you have a different view of the world, you may change this. Again, it's anyway a physically very questionable model. But this is kind of the assumption that the obstacles are kind of solid obstacles. Any other questions? If this is not the case, thank you very much. And we see each other next week, where we will look into the Kalman filter, which is one implementation of the Bayes filter. Thank you very much.